So I'll be talking about the plasma environment near the lunar magnetic anomaly regions and effect on the volatiles. Can I go next? So basically, the surface process by the solar wind can include ion sparring and implanting. So implanting can form new volatiles. For example, the hydrogen reacts with the oxygen on the lunar surface to create the hydroxyl, and the sparring can kick out these volatiles. So in general, on the lunar day side, the solar wind ions directly impact on the lunar surface with very high energy, about 1000 eV, to spark at the impact the surface because there's no global magnetic field. However, the crustal magnetic fields, also called the magnetic anomalies on the lunar surface, can alter the incoming solar wind ion bombardment and therefore alter the surface process. Next. So this is the global map of the magnetic field on lunar surface. So you can see here the red spot, the field strength can go up to several hundred nanotesla at the surface, and the size can be as large as the hundreds of kilometers. Next, please. So previous speakers, Georgia Kramer has talked about the spheres. So those are associated with the interaction between the solar wind and the magnetic anomalies. So the crustal magnetic fields can deflect, and even if it's strong enough, can stand off the solar wind plasma to create the density cavity, which can isolate the solar wind from bombardment on the surface. So the left image shows the spheres with the high albedo marks, shows a fresh surface. Linked to that same theory, it also has been found that the OH has relatively lower concentration on swirl regions than the off-swirl regions. Next, please. So basically here I divided the inaction mode into three regions in terms of the magnetic field strengths, the weak, moderate, and strong. When the magnetic field is weak, both electrons and ions are unmagnetized. So what you can expect is there's a small deflection of the charged particles. So when the B field is really strong, both electrons and ions are magnetized. The typical thing is the mini magnetosphere can form that I talked in the previous slide. So what we studied in our laboratory is the moderate strength of the B field, which is the electrons are magnetized, but the ions are unmagnetized. So the large charge separation can happen and create complex electric fields.50 please. So this is the laboratory setup. This is a vacuum chamber about 50 centimeters in diameter, 30 centimeters tall. And in the middle, there's the insulating surface, and under that, there's a permanent magnet to create the dipole field. And the dipole field was oriented in the vertical, parallel, and oblique to the surface. And below that, there's a hot filament creates plasma. And we have this probe to measure the potential distribution above the surface. So just mentioning that on the right side, I list a bunch of parameters. So the field geometry is about 6 centimeters in diameter and 6 centimeters high, which is much larger than the balance, about 1 millimeter to 4 millimeters. And also the electron gyre radius, it's less than 0.02 centimeters. So it's really small, but the ion gyre radius is much larger than 1 centimeter. The electrons are magnetized, but the ions are unmagnetized. Next one, please. So this is experiment 1. The B field is parallel to the surface. So this is potential contours measured above the surface along the dipole field. And it shows complex potential distribution. So I break it up into two profiles, vertical and horizontal. In the horizontal, you can see on the surface, there's large potential variation. The blue is more negative, the red is more positive. And in the vertical, in the center of the dipole, the potential on the surface is actually about 1 TI more positive than ambient plasma. And the TI in our experiment is about 1 eV, so it's 1 eV more positive. And also, interestingly, there's a potential minimum at about 1.5 centimeters above the surface. We also call the potential dip to create a non-monotonic shears. Next one, please. To explain that, we plot this surface potential profile along the dipole field. So I marked this extreme charging regions 1, 2, 3, 4. And the bottom is a drawing shows the dipole field and the particle trajectories. So the peak one is really positive, and that's caused by the shielding of the electrons. The electrons follow the field line shielded away from the center to the cusp at set. But the ions are unmagnetic, so the ions can still go to the surface and charge the surface to be positive. So we found it's 1 eV more positive because we have thermal ions. What we can expect that on the moon, the solar wind energy is about 1,000 eV of ions. So we can expect a very large positive potential on the lunar surface in some magnetic anomaly regions, which is the extreme charging region, never been observed. And so the electron follows the field line to the cusp, which is a small surface area. So it behaves like focusing. The electrons focus there and charge there more negatively. And before I talk peak 3, I will talk about peak 4 first. So what happens when it gets further out the dipole field, the B field gets weaker, so gyro radii gets bigger. And the electron can intercept the surface ahead of the field line. So then between the peak 2 and peak 4, and less electrons can go on there. So at peak 3, the potential will be charged more positively than peak 2 and peak 4. Next, please. So then what implication for us on the lunar volatiles from this potential distribution? So peak 2 and 4, they stay negative. So solid ions, so the surface process undergoes there. But at peak 1 and 3, the surface potential gets more positive. It can decelerate ions, especially at peak 1. If we expect large positive potential, it can significantly slow down the solar wind ions, and therefore the weakens the surface process a lot. And next, please. So experiment 2, this is the B field normal to the surface, and these blue arrows are magnetic field, and the white line field lines, so colors represent the potential. So again, at peak 1 on the surface, it's more positive. That's caused by the mirror reflection of the electrons. And the peak 2 is less positive, is actually more negative, and it's located at the edge of the cusp. So that's because the reduced effect of the mirror reflection of the electrons. And at peak 3, the field line basically parallel to the surface. So that I talked in the previous slide, the electrons shielded away and charged that region most positively. And then the peak 4, the electrons go to the cusp and may reflect back and follows lines to the side and charge the side of the dipole field more negatively. Next, please. So we studied this potential profiles in the central magnetic cusp in detail. So we had 2 permanent magnets and to create two dipole fields, so the red and blue, so we can make sure it follows something. So the red one, as the B field at the surface is about the same as the blue one, but it drops more quickly than the blue one. And there are three potential profiles, and the black one is without B field, and the red-blue correspond to red-blue B field. So it shows that the surface potentials in the B1, B2 both more positive than without B. So that's caused by the magnetic mirror reflection. And there's also okay, next. And there's also potential bounds at the locations. If you match them with the field streams profile, they're all about the same, 100 Gauss. And also that's a place where the field stream starts climbing rapidly. To explain that, next one, please. So we did modeling. So I list a bunch of equations, but I don't want to go into the detail about all these terms. Just let you know, we solved the Poisson's equation. We assume the ion flux is conserved. We assume the Boltzmann electrons, and the key point is this loss cone fraction, which tells how many electrons fall into the loss cone to the surface. And so the loss cone for those two dipole fields is supposed to be same because the B min, B max is same. But then we should expect same surface potential, but we see the difference. The blue one is much more positive. We think that's because of the collision. So electron collision in the cusp is more significant. It's much more significant, and we put that factor into the loss cone fraction, and we did the modeling. It agrees well with the data. Next, please. So again, the effect on volatiles. So peak 2 and 4 stay negative. So surface process on those, but peak 1 and 3 that's much more positive. That can weakens the surface process. Next one. So this is basically we turn the magnetic field 45 degrees. So what we observe is the asymmetric potential distribution that match the orientation of the dipole field. Also, you see a large variation in potentials on the surface that also can cause difference in surface process. Next. Next, please. Okay, in conclusion, so we have done a bunch of experiments to study how the dipole field altered the plasma surface interaction. And we found a great modification in the plasma environment near the surface. And we expect the same thing will happen on the moon. So we identified the magnetic shielding, focusing, and mirror reflection, and to create the complex potential distributions. So in some areas, extreme surface charging can form. So for example, this large positive charging in the center of the parallel dipole, and that can significantly alter the surface process. Thank you.
Type in your questions. Let's see, I'm not seeing So did you get ion entry all the way to the surface of these magnetic anomalies?
Yeah, so this model is ions are unmagnetized. They can just go to the surface. Okay, very interesting. Yeah, so the The interesting thing is like when people think strong magnomies can do something, like deflect the solar wind ions and keep the surface fresh. But actually, moderate strength magnetic anomaly can do the same thing too. If we think the ion, so they can shield the electrons and let ions go. So ions build up the charge, it can reflect that, the red ions. So then to reflect the bombardment.
You know, Andrew Poppy has modeled this, and we're seeing sort of an ambipolar electric field generate by the separation of the electrons and ions. In effect, is that potentially you're seeing that ambipolar electric field?
We don't see ambipolar, but you can imagine, so the ambipolar, this is built up above the surface. So the charge separation happen in our experiment is actually on the surface. So electrons share it out, but ions go to the surface. That builds the charge separation. And that creates the electric field pointing upward.
Uh-huh. This is really a sheath almost.
Yeah.
Got it. Got it. Jeffrey, we shared a question. Did you use the same definitions for weak, moderate, and strong as in the Blue et al. 2011?
Oh, I don't know simply. I just made up on my own. I should go back to check the paper and see.
All right. Okay. So you choose one of what your definitions are. Okay. So yeah. Okay. Yeah. So it's probably scaled though, right? Something scalable.
The matter interference is basically depend on the particle magnetizing. So how strong you can magnet both, magnet either of them, or magnet unmagnet, or both are unmagnet.
All right. All right. I'm not. Okay. I don't see any other questions.